Welcome to the video key for quiz 4B. So on this we have a question where we're looking at, the first question we're looking at what parameters we need to calculate the final temperature. So once again, we want to figure out the concepts before we try to calculate numbers. So if we think about a melting point curve, we could heat up a solid, melt the solid, heat up the liquid, melt the liquid, and then heat up the gas. So we've got gas, liquid, and solid, and then we've got melting, so going from solid to liquid, and we've got vaporizing, we're going from liquid to gas. Okay, so the question is, what do we have here? Well, here it says we're mixing ice at 0 degrees C, so we have ice, but it's just about to melt, so we can put a little dot here. All right, what about the water vapor? We have water vapor, so it's gas phase, but it's already at the temperature where it can condense. All right, so as soon as we see those dots, we can see that when we do this problem, we're going to need information about the heats of the phase transition. And we don't know where these arrows are going to meet without masses, right? Could be anywhere between these two dots. But in any case, whether they meet in the middle or in one of these flat segments, we can see that we're going to have a condensation segment, melting segment, and then we've got this where we're either heating or cooling water. So we do need the specific heat of liquid water, and we need the heat of fusion, because as soon as we start putting heat into ice at 0, it's going to start melting, so we need the heat of fusion. And as soon as we start taking heat out of water vapor at 100, it's going to start condensing, so we need the heat of vaporization. We don't need the specific heat of water vapor, because as soon as we cool the water vapor, as soon as we take any heat out, it's going to condense. It's not going to cool down any further because it can't get any colder than 100 degrees C. Same thing with the specific heat of ice. We don't need that, because if you put any heat into ice that's already at 0, it's going to melt. It's not going to change temperature. It can't get any higher. So we just need these three. Number 2, so we've got a substance in a beaker, and we're imagining taking this and having it melt and form a liquid. And we know that to do this is going to require heat. We're going to put heat into this. We can't melt something without putting heat into it. Okay, so if we're putting heat into it, then that heat had to come from the surroundings. So what we can say is that Q system is greater than 0, Q surroundings is less than 0. So if we take heat out of the surroundings, we're going to have to decrease its entropy. So the entropy of the thing we're melting goes up, but the entropy of the surroundings goes down. All right, a substance dissolves in water exothermically. What happens to the solubility of the substance if the temperature increases? So there's a couple ways of thinking about this. You can imagine, so you've got some substance, I'll just call it A, in a solid, and we're going to let it dissolve to form the aqueous version of this. So it could be a salt, it could be a molecule. And one way of thinking about this is like, oh, it's exothermic, this reaction gives off heat. And if you raise the temperature, it's going to push it backwards. But there's a more rigorous way of thinking about this, which is to remember that if we graph the log of the equilibrium constant for this process as a function of 1 over t, the slope is equal to negative delta H over R. So looking at this graph, we can see that we said it was exothermic, so delta H is a negative number. So that means the slope, since the slope is a negative of delta H over R, the slope has to be greater than 0. The slope has to be positive. So we draw a line like this. And looking at this, and I'll just write the equation for that curve over here. The log of K equilibrium is negative delta H over R times 1 over T plus delta S over R. So we can see that if we graph 1 over t as our x and the log of k equilibrium as our y, the slope is going to be that negative delta H over R. Okay, so anyway, what happens if we go to higher temperature? Remember, higher temperature is this way on the curve, right? Because it's a reciprocal temperature axis. So higher temperature means we go to smaller values of k, right? Smaller values log of k means smaller values of k. And so we end up with decreasing the solubility, right? The k for this reaction is going to get smaller, which means equilibrium is going to lie more and more towards the product. So if we were already at equilibrium, k equals q, but then we made k smaller, so now k is going to be less than q, reaction has to go backwards, right? It's going to be less soluble. Number 4, which thermodynamic parameters are always positive? So you want to think about what these processes mean. So solid solution is going to be going from salt, solid to salt, aqueous. Lattice is going from salt, solid to salt, gas phase. Or you could even a better way to say that might be to say various separated ions in the gas phase. Hydration is taking ions in the gas phase and putting them into water to make salt aqueous. And even there, it'd probably be better just to call this ions aqueous, right? Because the ions aren't connected to one another, they're floating around separately. Okay, so looking at these, we talked in the solubility lab about how we cannot predict the sign of delta H because delta H of solution, because you break a salt up, that costs energy, but then you hydrate the ions, that gives you energy back. So without knowing numbers, you can't say. So I'll put this one as a question mark. It is not positive. Lattice, you're going from ions that are bound to one another to ions that are flying around separately. You have to break ionic bonds to do that. That's the energy cost. This is going to be a positive number. Hydration, you're going from ions flying around in the gas phase to ions stuck in water inside of hydration spheres, and of course you're orienting the water when you make hydration spheres, so there's a lot of entropy loss here, so this is always negative. Lattice entropy, so we're going once again salt, crystal in the solid to ions in the gas phase, and so there's way more entropy. We're creating this gas phase, so this is going to always be positive. And delta S of solution is the combination of this step and this step. So you gain entropy when the ions, if you made ions a gas phase, we put the ions in the gas phase, but you're going to lose entropy when those ions are hydrated. So when you put those together without having numbers, you can't tell. So this is another question mark. All right, so the question just asked which ones were always positive. So we've got this one and we have this one. So the lattice enthalpy is always positive and the lattice entropy are always positive. You break up a lattice, you have to pay an energy cost, but you gain entropy. Okay, number 5. Consider a reaction with K greater than 1. What's the value of delta G standard? So you can think of this as a good reaction. It's product favored at equilibrium. We have higher concentration of products and reactants. And you know a good reaction is going to be one with delta G standard negative. We can make that more rigorous though by saying delta G standard is equal to negative RT log of K equilibrium. So we said we have a K greater than 1. So we plug in a number greater than 1 into this logarithm. That's going to be a positive number. Multiply that positive number times negative RT, we get a negative number for delta G standard. Okay, so a decrease in value, we're basically thinking about like a number line, and we imagine a number line here. So here's 0, get a different pen. And a decrease in value could mean that we're becoming less positive. It could mean we're becoming more and more negative. It could mean that we're switching over from positive to negative. So we've defined that any of those as being a decrease in value. Okay, so given that, we have to calculate, we have to see which one of these parameters would decrease in value. So let's start with the heat of solution. Actually, let's start with heat of solution. So heat of solution is a sum of the heat of hydration and the lattice enthalpy. So one of those is positive, one's negative. So we know the initial sign of this is going to be we don't know what it is. So the question is, what happens to it if we change the lattice, if we change the charge density? So we could put a dot anywhere on here. The question is, if we change to a salt with higher charge density, what's going to happen to that? And you know what? I'm going to go ahead and put lattice enthalpy on here, even though it wasn't, because it would be useful to talk about that. Okay, so lattice enthalpy is the energy cost to break apart a lattice. We know it's a positive number, and if we increase charge density, it's going to be harder to break apart that lattice, and so that number is going to get bigger. If we look at hydration, that's a negative number. It's exothermic because we're making bonds between, or at least IMFs, between the water molecules and the ions when we plunge them into water. This negative number gets bigger in size, right? So we have a bigger negative number and a bigger positive number. Now we can see, since one is positive and one is negative, we really don't know the sign of the heat of solution. And in fact, if we're making this negative number bigger with increasing charge density and this number bigger with increasing charge density, and since we're making a positive and negative bigger and it's a sum of those, we actually don't know if there's a trend there as well. So not only do we not know the sign of the heat of solution, there's not really a clear trend with changing the charge density. So let's look at the individual pieces, though. We did say that the heat of hydration is going to get more and more, it's going to get more and more negative as we increase charge density, right? So if we imagine this ion interacting with water, so I'm just going to draw water as little angles there, versus this ion, I'll call it a plus, I'll try to put a little +2 on here. If we had a +2 ion, that's going to interact with waters more strongly. We're going to be able to attract more waters to it. So that's going to make the heat of hydration even more exothermic. So it was already exothermic. It's going to get more exothermic. So it's going to be one of these arrows like that. So clearly this is an answer. What about the entropies? So once again, we can break the entropy of solution into two pieces. We can break it into lattice entropy and entropy of hydration. So lattice entropy itself is always a positive number, but it's not really affected by charge density because you're going from being locked into a lattice to going to a gas phase, and there's basically everything's locked in a solid in the crystal, and then it's free to move around in the gas phase, and so not really affected by charge density. So basically it's going to be a positive number, it's just going to stay a positive number. So this is not a clear trend. What about the hydration entropy? Well, remember, when you take ions in a salt and you plunge them from the gas phase into water, which is what hydration is, you're going to lose entropy in the ions, but you're also going to lose entropy in the water, right? The water becomes oriented. And that orientation effect gets stronger, it gets bigger as we go to higher charge densities. So delta S of hydration is always a negative number, and it's going to get even more negative if we increase charge density. So we define that as a decrease in value, so we got to circle this one. All right, so remember the entropy of solution, we said we could break into two pieces. We could break it up into lattice, and we could break it up into hydration. If we add those two, we get this. So we have one of that pieces does not have a trend. The other has a trend of more and more negative values, which means this is going to have a trend too. So the entropy change of solution, we can't say on the onset if it's positive or negative because we don't know the initial values of the hydration enthalpy and the lattice entropy. What we can say is that whether it's positive or negative, it's going to get more and more negative, or it's going to switch from positive to negative, or it's going to be less positive if we increase charge density. So the entropy change for dissolving a salt we can say gets worse if we increase charge density, which is why salts with high charge density are less likely to be soluble because of this effect. So there's 3 answers where we have a decrease in value with increasing charge density. Number 7, osmotic pressure. So osmotic pressure, it's like any colligative property, it's dependent upon the number of particles. So whether it's freezing point depression or boiling point elevation or osmotic pressure, all of these things are a function of concentration of the solute times the Van Hoff factor, right? Because the bigger the Van Hoff factor, the more number of particles you have. So it's this product. So all of these have the same concentration. So basically this is just saying which one of these solutions has the highest Van Hoff factor. So let's write the Van Hoff factor. Lithium nitrate, that's going to be 2 because you've got 1 lithium ion, 1 nitrate ion. Potassium sulfate is going to be 3 because you've got a -2 ion here, so that's going to give you 2 potassium ions for every formula unit. Hydrochloric acid is going to be 2. You dissolve this molecule in water and it splits up into chloride ion and hydrogen ion. What about acetic acid? Acetic acid is a molecule and it breaks up to form ions, but most of the molecules stay as acetic acid. So I'll just put approximately 1. It's going to be a little bit higher than 1, but not much. So looking at this, we can see that the clear winner is potassium sulfate because of its higher Van Hoff factor. Number 7, we need to find the delta H and delta S of this reaction. So this is just like the nitrate lab. We're going to use the Van Hoff equation. The log of K is equal to -1 or negative delta H of reaction over R is 1 over T plus delta S of reaction over R. So we can see this is going to be our intercept because we plotted this as our Y, and since we plotted this as our X, we've got Y equals mx plus b. Okay, so we can see that this is going to be our slope and our intercept is this. So we're just going to solve this equation. So we're going to say since our slope is equal to negative delta H over R, we can multiply by negative R and get delta H for our reaction is negative slope times R. We do have to be careful with our units here. So we're going to say, let's see, our slope was negative 3.16 times 10 to the third. What are the units? Well, remember slope is equal to rise over run. So the units are going to be the y units divided by the x units. So let's see, the x, well, that's unitless because that's a logarithm for the y. And for the x, we've got reciprocal Kelvin. So it's 1 over reciprocal kelvins. It's got units of kelvins. Okay, so we've got this many kelvins is our slope. And then we're going to multiply by, oh, we have to be careful. I almost made a sign error. There's a negative in this equation, and our slope was also negative, so we need a negative here. Okay, so this is going to be an endothermic reaction. Let's see, we have R 8.314. Whenever you're wondering which version of the gas constant to use, you check your units, right? So we can see that if we use this version, we're going to end up joules per mole, and that's what we want for delta H. Standard. So we multiply this out, So we get 2.63, 10 to the 4th joules per mole, or we could say that that is going to be 26.3 kilojoules per mole. Okay, so now we're going to do the entropy, and the entropy is going to be a similar process where we said that the y-intercept B was equal to delta S standard over R. So delta S is equal to R times the y-intercept B. And of course the y-intercept is going to have just the units of the y-axis, which is unitless. So we have 8.314 joules per mole per Kelvin times our y-intercept, which is negative 22.9 unitless. So we take our 22.9, we multiply it by 8.314, and we get 190. So we have 190 joules per mole per Kelvin. So the same units as R, and of course those are the units for entropy. Okay, so definitely make sure you check your units because you don't want to lose points on that. Okay, number 9. We're trying to figure out how concentrated a solution we can get. What's the solubility limit for silver sulfite? So we imagine taking a beaker and we're going to start dumping in this solid, and it's going to dissolve. We're going to stir and stir and stir, and we're going to keep going until we have solid left over. And that's how you know you have a saturated solution, right? If you have solid left over, you know that, and you've stirred it long enough, you know that whatever is up here in the solution must be a saturated solution because you've established this equilibrium. So we're trying to figure out what that concentration is of that saturated solution. So the way we do that is let me move this out of the way. Okay, so you can use a table. This kind of table might be overkill for some problems, but unless you're absolutely sure you're getting it right, I would go ahead and do it. Just it's worth the time because you'll make sure you get it right. So we're going to be dealing with concentrations and molarity. So we'll put a little reminder what our units are. And our goal is to come up with some expression where we're going to have, so we've got a K equilibrium. And so let's write K equilibrium for this reaction. It's going to be the concentration of sulfite ions at equilibrium, the concentration of silver ions at equilibrium. You got to square that because of this 2. And we put that over the bottom, but this is a solid. Okay, so the activities of pure solids and liquids are 1. They don't vary as the reaction progresses. So the reference state for solids is pure solid, and this is still a pure solid. No matter what we do during the reaction, although the concentration here might change out in the liquid, nothing happens down there. So this just stays in its reference state. So what we plug in here is something that tells us how far we are from the reference state. We're at our reference state, so that's just 1. So we could say divide by 1, or we could just leave it like this. On the other hand, these concentrations out here, they vary, right? When we first started, the concentration was 0, and as we approached equilibrium, we got higher and higher concentrations. So that's why these activities are not 1. Okay, so we have this. Our goal is to come up with some mathematical expression that relates these variables so that we can figure out what the equilibrium concentration is. So we'll put a little note to ourselves that we're going to start off at our initial state. We're going to see how much things change during equilibrium. And then we're going to get to equilibrium. So you could call it like I-check if you want, call it an I-check table. So we started off, in this case, we're looking at the solubility of silver sulfite in water. Now I could ask the solubility of silver sulfite in a sodium sulfite solution or in a silver nitrate solution. But I didn't. I asked in pure water, which means the initial concentrations of the ions are 0, right? There's no other ions in there at the start. And we're gonna cross this out since we're not going to end up plugging it into equilibrium. We don't have to worry about that. Okay, and you do that with any pure solid or liquid. So what about change? Well, we can see we're going to go forward because we can't go backward. We don't have any products. And we can see that for every time the reaction takes a step forward, every time we use up a mole of reactant, we're going to make 1 mole of sulfite ions. We're going to make 2 moles of silver ions. And since we're adding these to 0 at equilibrium, we just have 0 plus 2x and 0 plus x. Okay, so this equilibrium row is useful because we can feed this row right into this expression. Okay, so we have K equilibrium, and we've got to remember that whatever the concentration of silver is, we've got to square it. Well, what's the concentration of silver at equilibrium? It's 2x molar, so we can put 2x. Crucial that you use parentheses because whatever number is in here, you're going to have to square. Okay, so we're going to end up squaring that too. And over here we just have x, right? Because we have this x here. Okay, so we have this. So we can see it's x times 4x squared. So it's equal to 4x cubed. And all of that, I'll make that a better 3. So 4x cubed is equal to this. So now we have an equation with only one unknown, so we can solve it. We can say x is equal to K equilibrium. Because this is a salt solubility problem, this is often written as KSP, which means solubility product. It's just a variant of equilibrium. It's a subset of equilibrium. It's equilibrium when you're talking about dissolving a salt, but it's just another equilibrium constant. Anyway, so we take our K, we're going to have to divide it by 4, and then we're going to take a cube root. And you could say you're taking a cube root. You could just as easily write this as K. You could just as easily write this as K over 4 to the 1/3. That's the same as a cube root. So if you don't have a root key on your calculator, it's the same as taking it to the inverse power. Okay, very nice. So we're going to put in our number. We said we have 1.5 times 10 to the negative 14. And we divide it by 4, and then we're going to take a cube root. Okay, so when we do this, we got 1.5, 10 to the negative 14. Okay, and this isn't surprising. This is small k. We know that sulfites are not super soluble, especially with salts like silver. And we divide it by 4, and then we take a cube root. Okay, so I get 1.55, 10 to the negative 5th, and that is, remember everything in this table is in molarity, so we've got molarity. We're not quite done yet. We have to be careful. We have to look at what the question asks. The question asks, what's the concentration of silver ion? And the concentration of silver ion isn't x, it's 2x. So we've got to multiply our answer by 2. So we end up with the concentration of silver ion at equilibrium is equal to 2x, and that's equal to 3.1 times 10 to the negative 5th molar, or we could say, if we wanted to, we could say that's 31 micromolar or something like that. Anything like that is fine. That's the end of the video key for quiz 4. Thank you for watching.